welcome to Bay College's online lectures for college algebra. I'm Jim Helmer, and today we're going to look at section 5.1, which deals with polynomial functions. This is a relatively long section, so bear with me. If we're looking at a polynomial appears in a general form where we have a coefficient of x to the nth power, where n is the highest power of this, and it's written in descending order where this would be 1 less than this power, and this would be the corresponding coefficient, so it has the same subscript here as the power, just to indicate that this is the coefficient to that. And it is in descending order. This would be 2 less than the first, or 1 less than the next, and it continues down until we get down to a constant. Now, just for a moment, if we think about this, let's just say this is 4 for a moment. So this would be the power of 4, this would be 3, this would be 2. This, of course, is the first power. Well, what's the power of x here? Well, if we think about it, we can introduce an x to the 0 power, because anything to the 0 power is 1, making this just a constant. And notice it's a sub 0, which indicates the power of x is actually 0. So let's assess our polynomial function in a general form. Obviously, this is generic, where these are just n's representing some number. Our a's, no matter what they are, have to be some real value. And they can be 0. That just means that this degree wouldn't exist, and in descending order, this would be 2 less. That's all it means. And n, in order to be a polynomial, n has to be an integer greater than or equal to 0. Now, you notice it can equal 0 because that would be our last value, our constant. Our domain of all polynomials is going to be all real values. So our domain is any value of x that we can plug in, any real value. The leading term, well, that's n. The highest power is our leading term. And we generally want to write our polynomials in what we call descending order, where this is the highest power, followed by the next one, so on and so forth. Now, when we talk about the degree of a polynomial, the degree of a polynomial is defined by this leading power, this highest power. So the degree is the highest power, which in this case would be n. So this would be an nth degree polynomial. Now, I want you to note just for a moment here that these are not polynomials. And the reason why, well, there's a couple of reasons. Well, first of all, this would be x to the 1/2 power. So it's not an integer. So that would exclude it. Well, it also has a domain restriction. Notice our domains of our polynomials are always all real numbers. So this has a domain restriction. If we look at this, well, this also has a domain restriction. Even though that domain restriction is imaginary, it still has an x in a denominator. Its power, if we were to reduce this, its power would be to a negative value. Well, that's not greater than 0, right? Because if we think about it, let's not worry about these terms here. X over x squared would reduce to 1 over x. So x in the denominator, that means its power is less than 0. So it doesn't meet this criteria. And of course, here we have the reciprocal. Well, again, x in the denominator, we have a domain restriction. And its power, because this could be written as x to the negative first, is not an integer greater than 0. So these are not considered polynomials. And in the second example after this, we'll see where this actually applies. Now, let's talk about the degree of the polynomial. Let's carry this a little bit further here. Some examples we have, f of x equals 2. Well, its degree is actually 0. If we think about right here, this is just a constant. So I can say this is 2x to the 0 power. This is x to the 0. So we call it degree 0. Well, a common name for something like this, well, we recognize this to be a constant function. F of x equals a number, or y is 2. Y never changes. It's always 2. We call that the constant function. So that's a common name. Well, this one here, it's also degree 0, because I could say x to the 0, introduce an x value, so it is in a polynomial form, but it's x to the 0 power. It's just a constant. Well, this is a special constant. F of x equals 0. This describes our x-axis, where y is 0. We call this the zero function. All right, moving on, if we look at this polynomial here, well, its degree is 1, so it's a first degree. The highest power of the leading coefficient is 1. If we look at the, and we call this a linear equation, that's its common name. If we look at this, maybe we recognize this. We've covered this pretty in-depthly in the previous sections. If we look, our highest power is 2, so it's a second degree polynomial. And second degree polynomials are quadratics. If we notice, this is a quadratic in quadratic form, ax squared plus bx plus c, and we call that a quadratic. If we look at the next one, we notice it's a cubic function, or, well, it's, excuse me, I'm getting ahead of myself. Third degree, highest power of n is 3, and it is written in descending order, but we notice, hey, there's no x to the first power. Well, its coefficient just happens to be 0. Recall, we said a could be any real number. 0 is a real number, too. Well, we call this a cubic function. Lastly, or, you know, this could continue. We could continue with the higher ordered polynomials, but we'll end with this one here. We notice the degree is 4. You know, maybe it could be higher, but, you know, we only have limited time. So if we look at this, its degree is 4. And when it gets to 4 or higher, generally we just group them together and call them polynomials. Anything above 3 we'll call polynomial. You know, many numbers. That's essentially what it means. All right, so let's move on and see what can we determine when it comes to polynomials. Well, in order to be a function, a polynomial has to be a nice smooth graph with no domain restrictions, as we had saw in some of those notes there. Well, if it has no domain restrictions, that means infinite values of x, from negative infinity to positive infinity, are within our domain. And it has to be a smooth graph, which means if I were graphing it, I couldn't have any sharp turns or any areas where I'd have to lift my pencil off of the writing surface in order to continue drawing the graph. Now, if we look at this, our question is, are these polynomials? Well, the first one here, if I were to trace this, one nice smooth curve. I wouldn't have to lift my pen at all. The domain we can see as x goes to negative infinity, this just continues going down. If it goes to positive infinity, this continues to go up. So yes, this is a polynomial. Well, what about this? If we look at it, we notice, well, there's a piece over here and a piece over here. Well, I would actually have to lift my writing utensil off of the surface in order to continue this graph. So we can see, hey, there's a domain restriction. X is never equal to 0 in this graph here. So this is not a polynomial. Well, what about this? Is this a polynomial? Well, if I were to graph it, I have this sharp turn here. So it's not a nice, smooth graph. So this, hopefully we recognize this to be our absolute value library function. This is not considered a polynomial. Well, what about this? Here's a higher degree function. If we were to trace it, we can see, yep, nice smooth curves wherever I go here. This is considered a polynomial function. There's no domain restrictions. It goes from negative infinity to positive infinity, and we have, you know, a nice smooth curve here. So this would be a polynomial. Now, one thing about polynomials is power functions and end behavior. If we recall our library functions of some of our power functions, one example is the quadratic, which we've found is one of our polynomials, or maybe the cubic function. These are called power functions. Essentially, if we have f of x, some function, ax to the n, where n is greater than or equal to 1, we say, okay, well, this integer greater than or equal to 1 is a power function. As long as a isn't equal to 0, otherwise we'd have that 0 function, right? That's one of our constants. Now, it has some end behavior, and what we mean by end behavior is when it comes to our library function, as x goes to positive infinity or x goes to negative infinity, what does the graph behave as? Which of our library functions? Well, interesting enough, if n is an even number, it behaves just like our library function of a quadratic, or as if this were 2. 2 is an even number. So if n is even, essentially our polynomial power function is going to look quadratic. Maybe it's x squared, maybe it's x to the fourth, maybe it's x to the sixth, some even power. If the only difference is as the power increases, as long as it's even, it just gets narrower. Okay, so it has the same end behavior. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. They have the same end behavior. They both go to infinity in the y direction. So also, if we notice an even function, an even power function, has symmetry about the y-axis. Both of these two examples that I wrote here are symmetric with respect to the y-axis. Their domain, well, they are polynomial. I can put in any positive value of x or any negative value of x. I can put in 0 and get this point right here. So any real number. Its range is from its vertex, or its global lowest point, its minimum, or if it opened down, its maximum. So it's going to be from its min or max to infinity, or negative infinity, depending on which way it opens, right? Because we know all about these quadratics. Its end behavior, and this is something we're going to talk about just a little bit more. End behavior is which library function does it resemble? Well, since it's even, it resembles x squared in its end behavior. Both directions take you to y, positive infinity in the y direction. So that's its end behavior. What if n is odd? Well, if we recall our cubic function, because we know 3 is an odd number, it looks just like this. All of them are going to behave similarly if n is an odd number, if n is 5 or 7 or 9 or any higher ordered odd number. This has symmetry about the origin. So it's symmetric about the origin. Any point up here is reflected through the origin down here. Now, even if it was a higher degree, maybe it's 7th degree, so it looks something like that. It's compressed towards the y-axis. Its domain, well, I can put in any value in the negative direction or the positive direction or even 0. That's all real numbers. And that's one of the stipulations to be a polynomial. It must have an unrestricted domain. Its range, on the other hand, because as x becomes negative, it just continues on to negative infinity. And as x becomes positive, it goes to positive infinity. Its range in this case is all real numbers because it increases and decreases depending on which side of the axis we're on. But its end behavior is similar to the cubic function, our library function of x cubed. As x gets larger, y gets larger in the positive direction. As x gets negative, this goes in the negative direction. So the same end behavior. And when it comes to polynomials, we can do an end behavior test just by looking at the degree. What is this? Is it even or is it odd? And we can say this is going to be its end behavior. As x gets really large, it's going to increase or decrease, or in both cases increase, depending on if it's even or odd. And that's called the end behavior test, or the degree test. Now, let's talk a little bit about zeros and multiplicity. When it comes to zeros, our definition of zeros are x-intercepts. Well, let's take a look and find the x-intercepts here, the zeros. Well, to do that, we set the equation equal to 0. If I set this equal to 0, and I can do a little bit of factoring, essentially what we're doing is writing this as linear factors. X minus 3, x minus 2, these would be the linear factors. If I FOIL this together, I get that back. Now, it's important to know how to factor, especially in this section, because we're going to want to write are polynomials in linear factors if it does, in fact, factor. And now we could just use the zero value theorem. In order for this factor to be 0, x would have to be a positive 3. And in order for this to be 0, x would have to be a positive 2. These are my zeros. Now, if we notice, this factor only occurs one time. It's x minus 3 to the first power. It's only one linear factor. This is another unique linear factor that only occurs one time. We have an x term times an x term that gives us that x squared, our quadratic. Quadratic can factor into linear factors. And now we can graph it with this information. The thing about zeros and their multiplicity, and we'll talk a little bit more about multiplicity in a moment when we get to this one, but these have a multiplicity of 1. They only occur one time. That's what it means. Now let's go ahead and graph it. Well, we know the end behavior of x squared, well, that's a quadratic, so as it goes to infinity one way or the other, it's both going to increase in y, or go to the positive direction of y. So let's plot these points here. If this is 2 and this is 3, I know the end behavior from these points is going to increase. Well, what's happening in between here? Well, we could find its vertex and be more specific, but we just want to know the behavior of the function. Well, I know that it's going to be a parabola or parabolic, right? It's a quadratic, a square term, or an even term. Even if this was a fourth degree, I'd see that these do, in fact, open up, right? It's a polynomial, a quadratic that opens up of even power. So it looks like a parabola, which it does. Let's look at this example here. Now, this one's already factored. And if we think about it, what's the degree of this polynomial? Well, I have an x squared term times an x term. Well, x times an x squared, its behavior is going to be that of x cubed. So I know that it's going to go up and continue up depending on what side of the axis we're on. Now, if I look at this, well, let's use the zero value theorem. It's already in a factored form of linear factors. This 0 would be 1. 1 minus 1 is 0. 0 times anything is 0. So I'm essentially setting it equal to 0. What would make this factor, or these factors, because its power is 2, there's actually 2 of these linear factors. Well, its 0 would be negative 2. But it has a multiplicity, and I'll just abbreviate, a multiplicity of 2. That tells me something very important about the graph. Now, keep in mind, we could have other polynomials that have imaginary intercepts, but we're actually looking for the real ones, the ones that we can put on the graph. But those imaginary ones, they do tell us a little bit about the graph. Now, if we look at this, we have a 0 of 1 and negative 2. Well, if I have 1 here and negative 2 here, these are my zeros. What's my end behavior of this function? Well, an x squared times an x, we've already discussed, is x cubed, and I know the behavior of x cubed. Here, it continues on for infinity. Here, it goes down to negative infinity. Well, the only thing we're missing now is the area in between. Well, what we have to know about multiplicity, and we'll explore that in depth a little bit longer, is this 0, my negative 2, has even multiplicity. And what that actually tells me is that it only touches the axis. So it just touches at that point. It doesn't go into the positives. All right? And then, at some point, it has to turn and go across the x-axis to continue up. This has an odd multiplicity. It only occurs one time. 1's an odd number. So it passes through. Let's actually explore the definition of multiplicity and see what we're actually working with here. All right, multiplicity. If we have even multiplicity, which means the 0 is squared or to the 4th power or whatever its linear factor may be, if it's even, we say it has even multiplicity, it means that the polynomial touches the axis at that 0. So as an example, as we just saw, when it hit that negative 2, it only touched and then returned down from that value. All right, so at this value, c of 0, well, in this case, we're calling it negative 2, 0, right? That was our intercept that we found, our x-intercept. Even multiplicity means it just touches the x-axis. It doesn't cross the axis. Odd multiplicity says the polynomial does cross the x-axis at that value. Well, one of our zeros in that previous example was 1, but it only occurred one time. An odd multiplicity, 1 is an odd number. And we saw when we graphed it, it looked like this. It touched at this value, and it crossed through. So multiplicity can tell us a little bit about the behavior of the graph. What is it doing at those intercepts? Is it crossing the axis, or is it just touching it? Even touches, odd crosses. Keep that in mind. Let's look at this example here. F of x equals the linear factor x plus 3 to the 4th power and x minus 1 to the 3rd power. This has essentially two zeros. For this 0, x would be negative 3, but it has a multiplicity of 4. This 0 is positive 1. 1 minus 1 would be 0, but it has a multiplicity of 3. Now let's just assess this for a moment. What is the power of this function? What's the degree of this function? Well, I have x being raised to the 4th power times an x being raised to the 3rd power, so a total of x to the 7th. That's the highest degree of this, so I'm just going to write degree 7. So it tells me the behavior. I can actually graph this, or at least a sketch of the graph, with just this information. And I'll just do it right here real quick. If I have negative 3 with an even multiplicity, because 4 is an even number, I know that it's only going to touch at negative 3. I know that it has a 0 at positive 1 with odd multiplicity, which means it's going to pass through the x-axis. Now, degree 7, well, that's an odd degree, so its end behavior is similar to that to our cubic function. So I know that the cubic function, well, as x gets more negative, this is going to go to negative infinity in the y. As x gets positive, this goes to the positive y value. So that's its end behavior, just like a cubed function would do, because it's odd degree. Now, this negative 3 had an even multiplicity, so I know it doesn't touch the axis, it only crosses it. Or, excuse me, it only touches it, it doesn't cross because of even multiplicity. Then, we know at this one, so at some point it must turn and come back up in order to cross the axis to finish its end behavior, to be like a cubic function. All right, let's look at this one here. It says, a p of x with zeros of 1, negative 5 multiplicity 2, 4 multiplicity 3, and degree 6. All right, so if we do this one, let's say we have x minus 1. I'm going to write this polynomial out. I'm going to have x plus 5. Multiplicity 2 tells me it's squared. This one here says, oh, we have a 0 of 4. Now, you notice I'm changing the signs, right? Because we were saying, what does x have to be? Well, if x has to be 1, its h value or constant in here is the opposite of what you see in here. All right, and then this has multiplicity of 3, and it's of a degree 6. Well, if we think about this, here's an x to the 1st power, x being squared, that's 3 x's being multiplied. X to the 3rd, well, that's 3 more x's being multiplied. Yeah, that would be 6. 3, 4, 5, 6. 6 linear factors, or x to the 6th power. And we could take this information, we could graph it. Well, x to the 6th power, that tells me that its end behavior looks that of a parabola. It's going to continue on to infinity in both directions of y. Now, if we take our zeros here, well, I have a 0 of negative 5, so that's some value down here. I have a 0 of positive 1 and positive 4. And now I can say, well, what's its behavior at these zeros? Well, 1, I know, is an odd behavior, or excuse me, odd, because it only has a multiplicity of 1. That's an odd number. So it's going to pass through this axis. What's it doing at this 0 here, the negative 5? Multiplicity 2 says it just touches it. Well, its end behavior has to do something like that. It has to go up because our end behaviors, right, it's going to be like a parabola going in both directions. But because this is even multiplicity, I know it just touches. So it just comes down and touches the axis at negative 5. Here, this 0 of 4, right, across, we already discussed that. Sorry about that. This one, I haven't done yet, x minus 1. Well, the 0 of 1 only occurs once, odd, which means it passes through, so it has to pass through. And if we think about it, this eventually has to touch, and this would have to touch. And we can see this is essentially what our graph is going to look like. Now, the only exact values we have are the zeros, but now I know the behavior of the function. It's going to come down. It's decreasing until we get to this 0, and then it's increasing until we get to some maximum point, and then it's decreasing through this 0 to some minimum point, and then it's increasing as x goes to infinity. So I know its end behavior. All right, so here's your quiz. I want you to try doing this with this information. Find the polynomial, write it out as linear factors, with zeros of negative 2, 2, 3, and degree 3. So we have 3 zeros, 3 degree. That tells you something about its multiplicity. And once you've written out the polynomial, sketch a graph of that polynomial. Very similar to that, but it's only a 3rd degree, so it isn't too bad. All right, let's move on to the next topic. Now, one thing we saw in the previous example was something called turning points. And we haven't defined it yet, but we're about to. The degree of a polynomial actually tells us something about the behavior of that polynomial in between our zeros. N minus 1, where n is that highest power of the polynomial, if I subtract 1 from it, it will tell me the number of turning points. Now, in the previous example that I did, we had that for a 6th degree polynomial. Well, how many turning points did this one have? Well, it went from decreasing to increasing, that's 1. Increasing to decreasing, that's 2. Decreasing to increasing, that's 3. Well, it had 3 turning points, even though it was 6th degree. This tells me the maximum number of turning points, and I should specify that. It won't necessarily have that many, but it could. If you have a graph that has more than n minus 1 turning points, you know you've graphed something that isn't right. So let's look at this and see how can we use this information. Well, if we have a 1st degree polynomial, such as this linear equation, x minus 1, the maximum number of real zeros that it can have, because there's only one linear factor, is maximum of 1 real zero. Okay? The maximum number of turning points, well, if our highest power is 1, 1 minus 1 is 0, it can have no turning points. Well, that makes sense. It's a linear equation, which means it's a straight line. Straight lines never turn. So the maximum number of turning points would be 0. What if we have a degree 2? If we notice this was just a quadratic because I have an x times x. If I FOIL this out, let's just do that. X squared plus x minus 2. When I FOIL it out, we can see, oh, okay, there's our quadratic, and we know it's zeros. The maximum number of real zeros this can have, and since it's written as linear factors, we can see them, 2. 2 real zeros. Now, what about its turning points? Well, let's think about this. This is a parabola. Its shape, I'll just sketch it right there, goes from decreasing to increasing, which means it has 1 turning point. Well, that's why a parabola has this shape. Its max number of turning points is n minus 1. Well, 2 minus 1 is 1. 1 turning point forms a parabola. Now, if we look at this, our 3rd degree polynomial, maybe we have linear factor x minus 1 squared times x plus 2. So we have x squared times an x to the 3rd degree. That tells me that there are at most 3 number of real zeros. Well, we do have 3 zeros here. One of them has a multiplicity of 2. That tells me it just touches that axis. All right, and we could continue on to a fourth degree or higher. If we look at the example that we've had before, oh, I forgot about max number of turning points. Well, if it has 3 as its degree, it can have 2 turning points. Well, let's think about that cubic function. It can come up, but its end behavior is just like that. And that's exactly what this function would look like, because I know it has 1 turning point here and a 2nd turning point there, so that it continues down and upwards with that end behavior of a 3rd degree polynomial, a cubic polynomial. Fourth degree, of course, it would have 4 maximum number of real zeros, and the maximum number of turning points would then be 3. If we think about a 4th degree, and I'll just do it right here, it's going to look like that. We don't know what it's doing in between, but at most, it can have 3 turning points. Here's 1, 2, 3 turning points. Changes in directions from increasing to decreasing. Now, if we look at this here, when we graph this one, because of its multiplicity, when we graphed it in that sketch of the graph, we saw that, well, it only had 3 turning points, but it could have had at most 5, right? 3, 4, 5, 6 is our degree, so it could have at least 6 zeros, and it does. Some have multiplicity, but its turning points at most could be 5. But we saw that it actually had less than that. It only had 3 turning points. All right, let's move on here. And because I've run out of board space, and I am my own cameraman, it's easier to erase than it is to move the camera here. And if you're following along in the notes, we're essentially on the last page of the notes, and that's good news, right? It's the page we were looking for. Like I said, this is kind of a long section. Let's look at graphing this function. F of x equals x cubed minus 2x squared. Well, the first thing we're going to do is we're going to use the leading term test to determine its end behavior. Well, the leading term, we notice, is odd. It's cubed. So it's going to have end behavior that looks like a cubic function, right? So it's going to continue up and continue down. So we just did the leading term test. What is its behavior? Is it even or odd? It's odd behavior. All right, the next thing we're going to look at is we're going to factor this into its linear factors so we can find those zeros. Well, if I factor f of x, I look at these terms, I say, well, they have a common factor of x squared, and that would leave me with x minus 2. So I'm able to write it into, well, this squared factor and this linear factor. Well, this squared factor isn't so bad because when we set this equal to 0, we can find those zeros. So let's go ahead and find these zeros. X would be 0, but it has a multiplicity of 2, right? 0 squared is still 0. And the 0 for this one would be, well, 2 minus 2 is 0. So we have 0 with multiplicity of 2 and 2. Now, what we're going to do is we're getting ready to graph it. But let's first just look at the behavior on a number line. If I graph the zeros, okay, well, let's say this is 0, so that's where my y-axis will be. And then we have a 0 of 2, so let's say right over here, if this is 1, this is 2. What is the behavior at these zeros? Well, I know that it's a cubic function, so that it's 0 to the left, it's going to continue down, because that's what cubic functions do. At its furthest right 0, it's going to continue up. So now we have to determine what's the behavior in between there. Well, by finding these zeros, I kind of know what's happening here. This 0 of 0 has a multiplicity of 2. It just touches that axis. Well, it's coming up from the bottom, and it's only going to touch, which means at some point it's got to drop back down. And then this one, I know it's going to pass through, so it's going to come around and pass through the axis to continue in that upwards direction. Now let's find any y-intercepts. Well, how do we find y-intercepts? Well, if we're going to find a y-intercept, we just set x equal to 0. Well, that just happens to be one of our zeros. 0 times anything is 0. So when x is 0, y is also 0. So that's our y-intercept. We already found our x-intercepts, 0 and 2. Now we found the y-intercept. All right, and then we use the degree of the function to check, does this graph make sense? If we think about it, it's decreasing as x goes to negative infinity. It's decreasing in y. It's going to the negative direction. As x goes to positive infinity, y is increasing in the positive direction. So, yep, that's exactly what our cubic function does. So we're checking our degree. What about the number of turning points? Well, turning points, this is a third degree polynomial. It can have at most 2 turning points. Well, it goes from increasing to decreasing. It's a turning point right there. And then to come back up, it has to have another turning point because it goes from decreasing to increasing where it continues on. So it has 2 turns, 2 turning points, one here and one there. So we can see, and if we recall from Chapter 4, we talked about global or local maximums and local minimums. Those are the actual turning points. So if we were looking for those values, we could find the turning points as well. And then finally, we just put it all together on the graph, and we say that is the behavior of this function. I have its zeros. I know that it has 2 turning points, and I know its end behavior. Now, if I wanted to find something more, we could. We could find these values, and we'll see that when we get into next few sections here in Chapter 5. All right, so this has been Section 5.1, Polynomial Functions. Thank you for watching.